Unlocking the Mystery of Sargassum Blooms. How nutrient cycling drives massive seaweed accumulation, unlocking the mystery of sargassum blooms. How nutrient cycling drives massive seaweed accumulation for the second year running, the Caribbean islands, Gulf of Mexico, and northern South America have faced a negative record. An estimated 38 million tons of sargassum seaweed drifting towards their shores. This massive accumulation, particularly problematic during summer months, produces foul odors, deters tourism, and poses a threat to coastal ecosystems. While sargassum seaweed floating on the surface offers vital nourishment and habitat for marine species, its excess poses serious problems. But what fuels this dramatic growth? The Great Atlantic Sargassum Belt and the nutrient puzzle. The algae originate from the Sargasso Sea, east of Florida. However, since 2011, researchers have observed the growth of the Great Atlantic Sargassum Belt, a sprawling carpet of gulfweed that drifts from the equator toward the Caribbean, driven by easterly winds. Traditionally, scientists hypothesized that nutrient runoff from overfertilization and rainforest deforestation were responsible for the increase in sargassum biomass. However, these explanations proved insufficient to account for the observed growth. The key role of cyanobacteria and nitrogen fixation, a recent international study, led by the Max Planck Institute for Chemistry, has uncovered the primary mechanism driving these sargassum blooms. Researchers have identified crucial climatic conditions that facilitate the growth, enabling them to develop a system for predicting future sargassum stranding events. The study reveals that strong, wind-driven upwelling near the equator transports phosphorus to the ocean's surface. This increase in phosphorus availability directly benefits cyanobacteria, which colonize the brown algae and capture atmospheric nitrogen, converting it into a usable forma process called nitrogen fixation. This symbiotic relationship provides a competitive advantage over other algae in the equatorial Atlantic and explains past changes in sargassum biomass. Unveiling the past, coral cores as historical records to understand the connection between algal blooms, nitrogen fixation, and ocean conditions, researchers analyzed coral cores from various Caribbean locations. Corals incorporate chemical signatures from the water into their calcareous skeletons during growth, creating invaluable archives of past ocean changes. By examining annual growth layers, scientists can reconstruct past chemical compositions. The analysis of nitrogen isotopic composition in coral layers over the past 120 years revealed historic nitrogen fixation rates. Seawater samples calibrated these results, confirming that the coral records accurately reflect nitrogen fixation. A tightly linked phenomenon since 2011. Jonathan Jung, a Ph.D. student at the Max Planck Institute for Chemistry and the study's first author, explains, "We noticed significant increases in nitrogen fixation in 2015 and 2018, years of record sargassum blooms. Comparing these measurements with annual sargassum biomass data showed a remarkable alignment." The researchers found that algal growth and nitrogen fixation rates have been closely coupled since 2011, coinciding with the first significant displacement of brown algae from the Sargasso Sea into the tropical Atlantic. Ruling out other explanations and confirming the mechanism, the research team concluded that the excess of phosphorus is the key factor in sargassum blooms by eliminating alternative theories. Previous ideas suggesting that iron-rich Saharan dust or nutrient inputs from major rivers like the Amazon or Orinoco drove algal growth were deemed not correlated with the observed sargassum blooms. Predicting future blooms through climate observations, the study describes a mechanism wherein phosphorus from upwelling deep water and nitrogen from nitrogen fixation drive the sargassum blooms observed in recent decades. Understanding how cooler sea surface temperatures in the tropical North Atlantic and warmer temperatures in the southern Atlantic cause changes in air pressure, leading to wind anomalies and phosphorus-rich upwelling, can significantly improve predictions of sargassum growth. Looking ahead, the impact of global warming. According to researchers at the Max Planck Institute, the future of sargassum in the tropical Atlantic ultimately depends on how global warming affects the processes that control the supply of phosphorus to the equatorial Atlantic. Alfredo Martinez Garcia, group leader at the Max Planck Institute and the study's senior author, plans to expand these observations by analyzing new coral records from various Caribbean locations, aiming to guide efforts to mitigate the impacts of sargassum blooms on Caribbean reef ecosystems and coastal communities. Ultimately, the future of sargassum in the tropical Atlantic will depend upon how global warming affects the processes that drive the supply of excess phosphorus to the equatorial Atlantic. Alfredo Martinez Garcia, Max Planck Institute for Chemistry.